Welcome to Ultimate Sleep Doctor. Tonight, we'll explore a place of profound mystery, a realm where the very fabric of space bends. Black holes, born from the collapse of colossal stars, hold secrets at the universe's edge. They're points of infinite density, warping light and time itself. Consider the silence and vastness contained within these cosmic enigmas. It's beautiful, isn't it? This idea of such power hidden in the darkness. If you find yourself drawn to these quiet, monumental questions, we invite you to subscribe and share this journey with others. Just breathe. Let your thoughts drift, like stardust settling in the void. Let's begin. The universe, as we understand it, is built upon a beautiful, brutal dance of creation and destruction. Stars, those shimmering beacons of light and energy, don't simply exist forever. Their lives, though grand and spectacular, are bound by a fundamental law. They burn through their fuel. And when that fuel runs out, the consequences can be profound. Let's delve into the story of how some of the most enigmatic objects in space, stellar, mass black holes, are born, a process woven from the dying breaths of colossal stars. It all begins with a star, a giant, much larger than our sun. These aren't just any stars. They're often referred to as massive stars, typically at least 8 times the mass of our sun, and frequently exceeding 20. Their immense size is crucial because it dictates the extreme conditions needed for their eventual transformation. These stars are born in dense clouds of gas and dust, remnants of previous generations of stars that have already lived and died. Gravity, the ever-present force, pulls this material together, slowly increasing the star's density until nuclear fusion ignites within its core. This fusion process is the star's engine. It's a constant reaction where hydrogen atoms are fused together to create helium, releasing tremendous amounts of energy in the form of light and heat. This outward pressure generated by the energy pushes back against the inward pull of gravity, establishing a delicate equilibrium. For millions, even billions, of years, the star remains stable, steadily converting hydrogen into helium. It shines brilliantly, radiating energy across vast distances and providing a comfortable warmth to any planets orbiting within its reach. However, this peaceful existence is inevitably finite. The star's core, where fusion occurs, steadily burns through its hydrogen fuel. As the hydrogen depletes, the core begins to contract under the relentless force of gravity. This contraction increases the core's temperature and density, triggering a shift in the nuclear reactions. The core now begins to fuse helium into heavier elements like carbon and oxygen. This process continues, layer upon layer, with each successive stage producing heavier elements, neon, silicon, and eventually iron. Iron, however, is the star's doom. Unlike the previous fusion stages, fusing iron requires energy rather than releasing it. This is a critical turning point. With no outward pressure generated by fusion to counteract gravity, the core collapses inward with unstoppable force. The collapse happens incredibly rapidly, in a matter of seconds. It's a cataclysmic event, the fastest implosion in the known universe. As the core collapses, the outer layers of the star are violently expelled outwards in a spectacular explosion known as a supernova. This is not a gentle fading, it's a breathtaking, incredibly energetic release of all the star's remaining mass. The supernova's brightness can momentarily outshine entire galaxies. The intense heat and radiation rip apart the star, scattering heavy elements forged in the star's core and now infused into the expanding debris throughout space. These elements, essential building blocks for new stars and planets, become the seeds of future generations. But the story doesn't end there. At the heart of the collapsing core, something truly extraordinary happens. The gravitational forces are so immense that not even the repulsive forces of atomic nuclei can resist. The core continues to shrink, shrinking, until it reaches a point of infinite density, a singularity. This singularity is a region where our current understanding of physics breaks down. It's a place where space and time themselves become warped beyond recognition. Around this singularity, a region of space-time forms a black hole. This boundary is called the event horizon. It's a point of no return. Anything that crosses the event horizon, light, matter, even information, is irreversibly pulled towards the singularity. The gravity is so strong that nothing, not even light, can escape its grasp. The size of the black hole, specifically the radius of its event horizon, is directly proportional to its mass. The more massive the star that collapsed to form the black hole, the larger the event horizon. There are stellar, mass black holes ranging from a few times the mass of our Sun to upwards of 50 times the Sun's mass. Some theoretical models suggest even larger black holes exist, but their formation mechanisms are still being investigated. These black holes don't suck everything around them. They exert a strong gravitational influence, certainly, but only at close range. If our Sun were suddenly replaced with a stellar, mass black hole of the same mass, the planets in our solar system would continue to orbit as they do now, because their orbital paths are determined by the overall mass and distribution of matter. It's the proximity to the event horizon that creates the extreme gravitational effects. The existence of stellar, mass black holes provides crucial evidence for Einstein's theory of general relativity, confirming his predictions about the curvature of space-time. They are a powerful reminder of the dynamic, often violent, processes that shape the universe, and a testament to the incredible power of gravity. They are born from the death throes of giant stars, their existence a profound and beautiful consequence of the universe's relentless dance of creation and destruction. The accretion disk surrounding a black hole isn't just a swirling cloud of gas and dust. It's a region of profoundly warped space and time. We've already discussed how the immense gravity of the black hole itself is the core of this distortion. But to truly understand what happens near a black hole, we need to delve into the geometry of the event horizon. It's not simply about falling into something. It's about being fundamentally reshaped by the very fabric of space-time. Consider a trampoline. If you place a bowling ball in the center, it creates a dip. This dip represents the curvature of space-time caused by the bowling ball's mass. A marble rolled nearby will curve towards the bowling ball, not because the bowling ball is pulling it with a force, but because the surface itself is bowed. Similarly, a black hole, possessing an enormous mass compressed into an infinitesimally small point, creates a far more extreme curvature of space-time. The dip isn't just a curve, it's a violent, accelerating warp. The event horizon is the boundary of this warp. It's the point of no return, but it's also the location where the curvature of spacetime becomes so extreme that all paths, not just those aimed directly at the singularity, are inevitably drawn inwards. Time itself is affected. As you approach the event horizon, time slows down relative to an observer far away. This isn't a problem of speed. It's a consequence of how spacetime is distorted. The stronger the curvature, the more drastically time is affected. Let's use a thought experiment to further illustrate this. Imagine you're an astronaut approaching a black hole in a perfectly straight line. According to your own measurements, you're traveling at a constant speed. However, to an observer watching you from a safe distance, your movement appears to slow down dramatically as you get closer to the event horizon. This isn't because your personal time is slowing down. It's because the space around you is stretching and distorting so severely that your path appears to be getting increasingly prolonged. The mathematics describing this warping is complex, rooted in Einstein's theory of general relativity. The theory postulates that gravity isn't a force in the traditional sense. Instead, It's the result of mass and energy curving the surrounding space-time. The more mass, the greater the curvature. The curvature dictates how objects move, how light bends, how planets orbit, and, crucially, how time itself flows. The geometry around a black hole isn't just about the event horizon itself, it extends far beyond it, creating what's sometimes referred to as a causal horizon. This horizon isn't a physical boundary, but rather a theoretical limit. Within this horizon, the curvature of spacetime is so intense that the future and past become intertwined in a way that prevents any meaningful cause and effect relationships from being observed. Information cannot escape from within this region, and neither can signals be sent back out to the outside universe. Consider the mathematics again, the Schwarzschild metric, a solution to Einstein's equations for a non-rotating, uncharged black hole, describes precisely this warping. The equation itself is a complex formula, but it essentially predicts the gravitational field's strength at any given point around the black hole. The field strength is directly proportional to the mass of the black hole and inversely proportional to the distance from the event horizon. This means that as you get closer to the event horizon, the field strength increases dramatically, intensifying the warping of spacetime. Now, let's talk about light. Light, despite being massless, is also affected by this extreme curvature. It doesn't simply travel in a straight line, it follows the curves in spacetime. As light approaches the event horizon, its path bends dramatically, leading to a phenomenon known as gravitational lensing. The light from a distant galaxy, passing near a black hole, wouldn't travel in a straight line to your eye. Instead, the black hole's gravity would bend the light around it, creating multiple distorted images of the galaxy. The closer the light gets to the event horizon, the more extreme the bending, and the more pronounced the effect. Furthermore, the geometry isn't static, it's a dynamic, ever-changing process. The warping of spacetime isn't a fixed shape, it's constantly influenced by the black hole's mass and the motion of matter orbiting it. Even subtle changes in the orbit of an object near the event horizon can affect the curvature of spacetime, leading to complex and unpredictable changes in the gravitational field. The concept of a spacetime tunnel, a theoretical shortcut through warped spacetime, is often associated with black holes. While the idea is captivating, it's important to remember that the geometry is far more complex than simply a tunnel. The extreme curvature creates a network of interconnected paths, and attempting to navigate this network would be an incredibly challenging and potentially disastrous undertaking. The mathematics suggest that such a journey wouldn't be a smooth passage through space and time, but rather a violent and unpredictable experience, constantly subject to the intense gravitational forces. Ultimately, understanding the geometry of spacetime around a black hole reveals a truly awe-inspiring and profoundly strange realm, where the fundamental laws of physics are pushed to their absolute limits. The journey into the vicinity of a black hole isn't simply a descent through space. It's a profound alteration of reality itself, and at the heart of this shift lies a bizarre interaction between observation and the very fabric of spacetime. Before we delve into the specifics, let's consider something fundamental about the universe. As we understand it, everything, from the tiniest particle to the largest galaxy, interacts with electromagnetic radiation, light, radio waves, rays, you name it. This interaction isn't always passive. Simply by measuring something, by attempting to see it, we inevitably change it. This is the observer effect, a cornerstone of quantum mechanics, and its implications near a black hole are extraordinarily dramatic. The closer you get to a black hole, the more intense the gravitational field becomes. This isn't just a matter of increased force, it fundamentally warps space and time. Einstein's theory of general relativity tells us that gravity isn't a force in the traditional sense, but rather a consequence of mass and energy curving spacetime. Think of spacetime like a stretched rubber sheet. If you place a heavy ball on it, the sheet dips down. That dip represents gravity. Other objects rolling nearby will follow the curve. Now, imagine that sheet is incredibly warped, as it would be near a black hole. The curvature is so extreme that time itself is affected. Let's consider a hypothetical observer. Let's call him Elias, bravely, or perhaps foolishly, approaching a stellar, mass black hole. Elias is equipped with a highly sensitive instrument, a sort of advanced telescope, designed to measure the faint light emanating from matter spiraling towards the event horizon. As Elias ventures closer, the light he's attempting to observe begins to behave strangely. Due to the immense gravitational field, photons, thus light particles, lose energy. This isn't a simple reduction in intensity, it's a fundamental shift in their behavior. Each time a photon interacts with the incredibly dense matter surrounding the black hole, it loses a tiny bit of its energy. This energy loss isn't random. It's directly linked to the observer's measurement. The act of Elias's telescope trying to capture this light to analyze its wavelength and intensity forces the photons to interact with the surrounding spacetime in a way that exacerbates the energy loss. It's like trying to measure a rapidly moving river with a very sensitive scale. The act of weighing the water alters its flow, changing the measurement itself. The more intently Elias focuses on the light, the faster it loses energy, and the more distorted spacetime becomes around him. Now, let's zoom in on the extreme effects near the event horizon. As Elias approaches the edge, the time dilation becomes truly remarkable. From the perspective of a distant observer, someone far away from the black hole, Elias's clock appears to slow down dramatically. This isn't a visual effect, it's a fundamental distortion of time itself. The intense gravity is stretching out time, causing Elias's movements and processes to appear to take significantly longer than they would for someone in a weaker gravitational field. The closer Elias gets, the more pronounced this effect becomes. At a certain point, just short of the event horizon, the time dilation is so extreme that a second of time for Elias might correspond to years, decades, or even centuries for the distant observer. It's a terrifying, beautiful consequence of spacetime's curvature. Elias wouldn't necessarily feel like time was slowing down for him. His biological processes would continue at their normal rate. However, his signals, any data transmitted back to the distant observer, would be drastically shifted in frequency, appearing to arrive at an incredibly slow pace. Furthermore, the observer effect isn't just about energy loss and time dilation. It's about the very geometry of spacetime. The intense gravity warps spacetime so severely that the path a photon takes isn't a straight line. Instead, it's forced into a swirling, helical path, an effect known as gravitational lensing. Elias's telescope, trying to maintain its focus on the light, is actively contributing to this distortion. The measurements he's taking aren't reflecting the true behavior of the light. They're influenced by his observation itself. As Elias crosses the event horizon, the point of no return, the observer effect becomes infinitely complex. Within the event horizon, the gravitational forces are so extreme, and the spacetime curvature so profound, that our conventional understanding of space and time breaks down. It's a region where the laws of physics, as we know them, cease to apply. The act of observation becomes utterly meaningless, and the fate of Elias is, quite literally, beyond our ability to comprehend. The journey into a black hole isn't simply a physical one. It's a journey into a realm where reality itself is shaped by the act of looking. It's a stark reminder that our observations are not passive recordings of the universe, but active participants in its construction. and near the most extreme gravitational environments, like those found around black holes. This interaction takes on a scale that challenges the very foundations of our understanding of space, time, and existence. For decades, the prevailing image of a black hole was one of absolute darkness, a cosmic abyss where even light couldn't escape. This was built upon Einstein's theory of general relativity, which beautifully described gravity not as a force, but as a curvature of spacetime. A sufficiently massive object, like a collapsed star, would warp spacetime so drastically that everything around it, including light, would inevitably plunge inward, never to return. But in the 1970s, a young physicist named Stephen Hawking challenged this fundamental understanding, proposing a revolutionary idea: black holes aren't entirely black. He suggested they emit a faint, persistent glow, a phenomenon now known as Hawking radiation. Hawking's inspiration came from a deep dive into the quantum world, a realm governed by rules vastly different from those of gravity described by general relativity. Quantum mechanics tells us that empty space isn't truly empty. Instead, it's teeming with virtual particle-antiparticle pairs that constantly pop into existence, and then almost instantly annihilate each other. These aren't like the particles we see in our everyday world. They exist for fleeting moments, borrowing energy from the vacuum before vanishing back into nothingness. The duration of their existence is limited by the uncertainty principle, a cornerstone of quantum mechanics which dictates that we can't know both the energy and the time a particle exists with perfect precision. Hawking realized that near the event horizon of a black hole, the point of no return, these virtual particle-antiparticle pairs could be affected in a particularly dramatic way. Normally, a virtual particle-antiparticle pair would appear and then annihilate each other. However, close to a black hole's event horizon, the intense gravitational field can disrupt this process. One particle of the pair might fall into the black hole, while its partner escapes. It's crucial to understand that this escape isn't a simple act of light radiating outward. The escaping particle doesn't carry any information about the black hole itself. It's effectively a spontaneously generated particle, created from the quantum vacuum, not a reflection of the black hole's interior. This is a profoundly strange consequence of quantum mechanics. The black hole isn't actively emitting anything. It's more like the event horizon is scavenging the quantum vacuum, taking advantage of these fleeting, temporary fluctuations. The key to quantifying this process lies in the area of the event horizon. The size of the event horizon is directly related to the rate at which Hawking radiation is emitted. A larger event horizon means a faster emission, and vice versa. This relationship is elegantly expressed by Hawking's equation, which describes how the mass of a black hole decreases over time due to this radiation. Now, let's consider the implications of this emission. Because the radiation is incredibly faint, it's extremely difficult to detect. The temperature of this radiation is inversely proportional to the black hole's mass. Smaller black holes have a higher temperature and emit radiation at a higher rate, appearing almost like a tiny, radiating star. Larger black holes, with their immense gravitational fields, have much lower temperatures and emit radiation at a rate so minuscule that it's almost undetectable. For stellar, mass black holes, formed from the collapse of massive stars, the Hawking radiation is far too weak to observe directly. The black hole's mass decreases so slowly that it's practically frozen in time. However, theoretically, over an incredibly long period, far longer than the age of the universe, a stellar, mass black hole would slowly evaporate entirely through Hawking radiation. This evaporation process isn't like a sudden burst of energy. It's a gradual, persistent loss of mass, accompanied by a corresponding decrease in temperature. As the black hole shrinks, it becomes hotter, radiating more intensely, and eventually, it disappears completely. The last photons emitted during this final stage would be incredibly energetic, carrying away the remaining momentum and energy of the evaporating black hole. The theoretical lifespan of a black hole depends directly on its mass. Smaller black holes have shorter lifespans, while larger ones can theoretically persist for far longer. This raises some fascinating and admittedly speculative questions. If a black hole were to eventually evaporate, what would happen to all the information about the matter that fell into it? General relativity suggests information is lost, a concept known as the information paradox. However, recent theoretical developments, particularly those related to quantum entanglement and holographic principles, suggest that information might be encoded on the event horizon itself, constantly fluctuating and re-emerging as the black hole evaporates. The exploration of Hawking radiation is a beautiful example of how seemingly disparate branches of physics, gravity, and quantum mechanics can be brought together to provide a deeper, more complete understanding of the universe. It challenges our most fundamental assumptions about black holes, transforming them from absolute voids into dynamic, radiating entities, slowly fading away into the quantum fabric of spacetime. The ongoing research into this phenomenon continues to push the boundaries of our knowledge and offers tantalizing glimpses into the ultimate fate of these cosmic giants. The universe isn't a silent, empty void, despite what some might believe. It's a place of constant motion, of materials swirling and colliding, of energy transforming in ways we're still only beginning to fully grasp. And at the heart of this activity, particularly around black holes, lies a fascinating process called accretion. It's how black holes, those seemingly passive absorbers of everything, actually gain mass and energy. Let's consider a black hole not as a simple pit in space, but as the gravitational anchor of a vast, swirling region. This region isn't empty. It's filled with gas, dust, and even entire stars pulled inexorably towards the event horizon, that boundary beyond which escape is impossible. As this material gets closer and closer, it doesn't simply fall straight in. Instead, something remarkable begins to happen. The intense gravity creates a distorted, chaotic dance. This dance is the genesis of what we call an accretion disk. Visualize a spinning pizza dough, but instead of toppings, you've got matter: hydrogen, helium, carbon, oxygen, everything from interstellar space being pulled towards the black hole. As this material spirals inwards, it doesn't move in a straight line. The black hole's gravity is so powerful that it's constantly bending and tugging on the material, forcing it into a flattened, rotating disk. The closer the material is to the black hole, the faster it orbits. Imagine a water wheel. The water at the center spins much faster than the water further out. This difference in speed generates tremendous friction between the particles within the disk. This friction isn't a gentle rub. It's a colossal collision event happening on a microscopic scale constantly. Electrons and protons, stripped of their electrons in the intense environment, are forced together, forming ions. These ions collide with each other and with the surrounding gas, generating an enormous amount of heat. This extreme heat causes the material to radiate intensely, primarily in the form of X-rays. That's why, despite being surrounded by darkness, many black holes are revealed through the intense X-ray emissions from their surrounding disks. But the story doesn't end with heat. As this superheated material spirals inward, something even stranger happens. Powerful magnetic fields become tangled and amplified. The rotating disk, coupled with the immense gravity, creates incredibly complex magnetic fields. These fields aren't just passively influencing the motion of the material, they actively channel it. Think of it like a river flowing around a rock. The water finds the path of least resistance. and the magnetic fields guide the material along specific pathways within the accretion disk. Now, this is where things get truly spectacular. The magnetic fields aren't just shaping the disk. They're launching powerful jets of plasma outwards, perpendicular to the disk's plane. These jets, often extending for thousands of light years, are beams of incredibly energetic particles, electrons, protons, and magnetic fields traveling at near the speed of light. The mechanism behind jet formation is still being intensely studied, but the prevailing theory involves the twisting of magnetic field lines around the black hole. As the plasma spirals inward, the magnetic field lines are stretched and twisted, and the energy released from this process is channeled into these focused beams. The process isn't a uniform outpouring. The jets are remarkably collimated, meaning they're squeezed into narrow, highly focused streams. It's as if the black hole is using its gravity and magnetic fields to sculpt these jets, directing them outwards. The composition of the jets can vary depending on the black hole, and their power can fluctuate dramatically. Some jets are relatively faint, while others are among the most luminous objects in the universe. These jets play a crucial role in the evolution of galaxies, particularly active galactic nuclei, AGN, which are powered by supermassive black holes at the centers of galaxies. The energy released by the jets can heat the surrounding gas, suppressing star formation in the galaxy. It's a complex feedback loop. The black hole feeds, the jet influences the galaxy, and the galaxy then provides more material for the black hole to consume. Furthermore, observations have revealed that some of the material ejected in these jets doesn't simply disappear into space. It can fall back onto the accretion disk, providing additional fuel for the black hole. This creates a continuous cycle of accretion, jet formation, and material return, sustaining the intense activity around the black hole for potentially millions of years. The study of accretion disks and jets around black holes is pushing the boundaries of our understanding of gravity, magnetism, and the dynamics of extreme environments. They demonstrate that even the most seemingly passive objects in the universe can be incredibly active, dynamic systems constantly transforming matter and energy in ways that are both beautiful and awe-inspiring. It highlights that the universe is not a static place, but a realm of continuous change and interaction, driven by forces we are only beginning to fully comprehend. The universe isn't always a straightforward, perfectly clear picture. Sometimes it's like looking through a rippled glass, or perhaps through a massive, invisible lens. This distortion, this bending of light, is one of the most fascinating and dramatic consequences of black holes' extreme gravity. It's a phenomenon called gravitational lensing, and black holes are, arguably, the most powerful lenses in existence. The story of gravitational lensing begins with Einstein's theory of general relativity. This theory describes gravity not as a force pulling things together, but as a curvature of space-time itself. Think of space-time like a giant, stretchy sheet. Massive objects like planets, or crucially black holes, create a deep dip or well in this sheet. Now, if you roll a marble across this sheet, it won't travel in a straight line. Instead, it will curve around the dip, following the shape of the warped space-time. Light behaves in a similar way. Photons, the tiny particles that make up light, also follow the curves of space-time. When light from a distant galaxy passes near a black hole, the black hole's immense gravity bends the path of the light. It's not that the black hole is actively pulling the light in. It's that the black hole is warping the very fabric of space around it, and light simply follows that warped path. This bending can produce a remarkable effect: multiple images of the same distant galaxy, or even a ring of light surrounding the black hole, a phenomenon known as an Einstein ring. The degree of bending depends on how much mass the black hole possesses and, crucially, on the alignment between the observer, the black hole, and the distant galaxy. The closer the alignment, the more dramatic the lensing effect. If the alignment is perfect, the galaxy appears as a complete circle of light, with the black hole sitting at the center, creating the iconic Einstein ring. These rings are incredibly valuable to astronomers because they provide a direct, albeit distorted, way to study the mass and distribution of matter around the black hole. It's important to note that this isn't just a visual trick. The bending of light alters the way we perceive the distant galaxy. The light from different parts of the galaxy arrives at our telescopes at slightly different angles, creating a smeared out image. The colors of the light can also be affected. Blue light, having shorter wavelengths, is bent more strongly than red light, which has longer wavelengths. This separation of colors, called chromatic aberration, can be another clue to the gravitational effects at play. Detecting gravitational lensing caused by black holes is a challenging task. Because the lensing effect is so subtle, astronomers use sensitive instruments like the Hubble Space Telescope and the James Webb Space Telescope to search for these distortions. They look for subtle shifts in the positions of background galaxies, for changes in their colors, and for the potential appearance of Einstein rings. The most dramatic examples of black hole lensing occur when the black hole lies directly between us and a distant galaxy. Sometimes, the galaxy appears distorted into arcs or multiple images. However, black holes aren't the only objects that can act as gravitational lenses. Massive galaxies and clusters of galaxies can also produce significant lensing effects, creating distorted arcs and rings around them. But black holes, with their immense density and gravity, provide the most intense and detailed lensing. Scientists are using gravitational lensing by black holes to study objects that would otherwise be too faint or too distant to observe directly. By analyzing the distorted images, they can estimate the mass of the black hole and the distribution of dark matter surrounding it. Dark matter, which makes up a significant portion of the universe's mass, but doesn't interact with light, is often revealed through its gravitational effects. Furthermore, gravitational lensing isn't just a passive observation tool. It's becoming a powerful way to probe the early universe. Light from galaxies that formed very early in the universe has been traveling towards us for billions of years. As this light passes by massive objects, like black holes, it gets distorted and magnified, allowing astronomers to study these distant galaxies in unprecedented detail. The study of gravitational lensing is constantly evolving as new telescopes and instruments become available. With each discovery, our understanding of black holes and the universe expands. It's a testament to the ingenuity of scientists and the remarkable way that light, gravity, and space-time are intertwined. The universe's secrets, often hidden behind the extreme gravity of a black hole, are slowly being unveiled, one distorted image at a time. It's a reminder that the cosmos holds endless surprises, waiting to be discovered through careful observation and scientific inquiry. The universe, as we've explored, is a place of extraordinary extremes. We've seen how black holes, those regions of spacetime where gravity reigns supreme, aren't simply cosmic vacuum cleaners. We've witnessed their hunger satisfied by swirling accretion disks and the spectacular jets they launch into space. We've even observed how their immense gravity bends and distorts the very fabric of the cosmos through gravitational lensing. But despite all this fascinating activity, there's a surprisingly simple and elegant idea that helps us understand black holes on a fundamental level: the no-hair theorem. It began with Kurt Gödel, a brilliant mathematician who, along with Carl Schwarzschild, made a groundbreaking initial discovery. Schwarzschild, shortly after Einstein published his theory of general relativity, was the first to accurately describe the shape of a non-rotating black hole. His solution, a set of equations, predicted the existence of a boundary, the event horizon, beyond which nothing, not even light, could escape. However, Schwarzschild's solution also included a bizarre, and at the time, unexplained, term. This term represented an incredibly large and seemingly arbitrary amount of energy and angular momentum, basically spin associated with the black hole. It was like the black hole was constantly shedding energy and spinning, but the amount was utterly baffling. The problem was that this added information didn't seem to provide any actual new details about the black hole itself. It was as if the black hole was carrying a vast, unseen baggage. Scientists were left wondering what else was influencing the black hole's behavior beyond its mass and the size of its event horizon. This nagging question fueled decades of research. Then, in the 1970s, physicists Roger Penrose and John Wheeler independently arrived at a revolutionary conclusion. They realized that this seemingly extraneous term in Schwarzschild's solution wasn't just a mathematical quirk. It represented a fundamental limitation. They proposed that a black hole, once formed, possesses only three independent properties: its mass, its electric charge, and its angular momentum, its spin. That was it, nothing else. This became known as the no-hair theorem, named after the concept of hair. A black hole has no further distinguishing characteristics. Think of it like a perfectly blank canvas. Once a black hole forms, it becomes incredibly efficient at erasing all information about the matter that fell into it. The immense gravitational forces crush everything: matter, energy, even the intricate details of its composition, into a singularity, a point of infinite density at the black hole's core. But crucially, this process leaves no trace behind. The theorem doesn't say that we can't know a black hole's mass, charge, or spin. We can, through observation, perhaps by tracking how it interacts with surrounding matter, or by observing its gravitational effects on nearby objects. But the theorem states that these are the AV-only measurable properties. Any other information about the star, gas cloud, or whatever collapsed to form the black hole is lost forever. The implications are profound. It dramatically simplifies our understanding of black holes. Before the no-hair theorem, scientists struggled to account for the countless possible ways a black hole could differ depending on its history. Now, we can describe any black hole, regardless of its origin, using just these three parameters. It's like saying that all cats, regardless of their breed, color, or personality, are still fundamentally cat. Consider a supernova, a massive star's explosive death. The core collapses under its own weight, forming a black hole. The black hole inherits the mass of the original star. It also inherits any angular momentum the star possessed. This would have been built up over the star's life from the rotation of its outer layers. And, crucially, it inherits any electric charge that may have accumulated. That's it. All the complex details of the supernova's chemical makeup, the specific motions of the star's gas, everything is compressed and lost within the black hole. The no-hair theorem doesn't solve all the mysteries surrounding black holes. It doesn't explain what happens to information that falls into the singularity. This remains a central puzzle in theoretical physics, linked to the concept of information loss and potential connections to quantum mechanics. However, it provides a remarkably elegant and accurate framework for describing black holes, allowing us to focus on the most fundamental aspects of their existence. Furthermore, the theorem has spurred research into the possibility of quantum hair. Speculative ideas that suggest subtle quantum effects might actually leave a trace on black holes, perhaps encoded in the behavior of particles near the event horizon. These are actively investigated areas of research, driven by the desire to reconcile general relativity with quantum mechanics and to potentially resolve the information paradox. So, As we continue to explore the cosmos, remember that even the most seemingly chaotic and destructive objects like black holes can be understood through a surprisingly simple set of rules. The no-hair theorem reminds us that sometimes the most profound truths can be found in the most concise descriptions. It's a testament to the power of mathematical precision and the enduring quest to unravel the universe's deepest secrets. The universe, we've discovered, isn't simply a cold, empty void. It behaves, in surprising ways, according to the laws of physics, and those laws sometimes suggest heat, order, and even pressure, even where we once believed only emptiness reigned. Black holes, those enigmatic regions of spacetime where gravity is so intense that nothing, not even light, can escape, are particularly fascinating in this regard. For decades, the prevailing view was that a black hole was simply a featureless abyss, a perfect sphere of infinite density. But the 20th century brought a revolution in physics, particularly through the work of physicists like Jacob Bekenstein and Stephen Hawking, who began to grapple with the idea that black holes weren't quite so simple. They began to explore what we now call black hole thermodynamics. The initial shock came from Bekenstein's thought experiment in 1973. He realized that if you applied the laws of thermodynamics, which state that energy is conserved, and that systems tend towards disorder, to a black hole, things started to get strange. He reasoned that if you were to somehow heat up a black hole, you would need to add energy to it. But where would that energy go? The standard rules of thermodynamics suggested that energy would be distributed throughout the black hole's volume. However, the sheer density of a black hole, particularly its event horizon, the point of no return, presented a fundamental problem. If you tried to add energy, it would simply collapse inward, becoming part of the black hole's mass. This led Bekenstein to propose a revolutionary idea that the black hole's surface area, not its volume, was the fundamental measure of its capacity to store energy. This concept was completely counterintuitive. Normally, we think of heat and energy being associated with volume. But Bekenstein argued that the event horizon, with its immense surface area, represented the black hole's skin, and that this skin was directly related to the amount of energy the black hole could hold. He calculated a relationship, now known as the Bekenstein-Hawking area law, which states that the entropy, a measure of disorder or randomness, of a black hole is proportional to the surface area of its event horizon. Entropy, in this context, wasn't about the black hole's contents, it was about its potential to harbor information and, consequently, energy. A larger event horizon meant a higher entropy. Stephen Hawking built upon Bekenstein's work with a truly groundbreaking prediction in 1974. He demonstrated that black holes weren't entirely inert. He showed that black holes weren't simply absorbing energy. They were actually emitting it. This emission takes the form of radiation, now known as Hawking radiation. Hawking's calculations, based on quantum mechanics, revealed that due to quantum effects near the event horizon, particle-antiparticle pairs are constantly popping into existence and immediately annihilating each other. However, sometimes one particle of the pair falls into the black hole while the other escapes. To an outside observer, this escape appears as a stream of thermal radiation. Essentially, the black hole is radiating away energy, and therefore, temperature. The temperature of a black hole, according to Hawking, is inversely proportional to its mass. Smaller black holes are hotter, radiating away energy at a much faster rate, while larger black holes are cooler and radiate much more slowly. This means that a stellar, mass black hole would be incredibly hot, while a supermassive black hole at the center of a galaxy would be chillingly cool. This constant emission process, this thermal equilibrium, fundamentally changed our understanding of black holes. It demonstrated that black holes weren't just sinks for information or energy, They were active participants in the universe's thermal landscape. Furthermore, the process of Hawking radiation leads to the gradual shrinking of a black hole over an immense timescale. As the black hole emits energy, its mass decreases, causing the event horizon to contract slightly. This contraction, in turn, reduces the Hawking radiation, leading to a new, smaller equilibrium. This self-regulating process, driven by temperature and entropy, implies that black holes aren't eternal, inexhaustible engines. They are, over an unimaginable period, destined to evaporate completely, radiating away their mass as heat. The concept of pressure within a black hole is also surprisingly relevant. General relativity predicts that immense gravitational forces generate tremendous pressure within these regions. This isn't just a simple compressive force, it's a pressure stemming from the curvature of space-time itself. The intense gravitational field creates a tension within the fabric of space-time, contributing to the overall pressure. While directly measuring this pressure is, of course, impossible, theoretical calculations based on the extreme space-time distortion provide a framework for understanding it. This pressure, combined with the thermal pressure arising from the Hawking radiation, adds another layer to the complex thermodynamics of black holes. The study of black hole thermodynamics continues to be a vibrant area of research, pushing the boundaries of our understanding of gravity, quantum mechanics, and the fundamental nature of the universe. The realization that black holes aren't simply voids, but active thermodynamic objects, radiating energy and slowly evaporating over vast stretches of time, reveals a universe far more complex and fascinating than we had previously imagined. The universe, as we've begun to understand, is a remarkably complex dance of gravity and space-time. But even with our grasp of thermodynamics and the no-hair theorem, describing the full story of a black hole's existence from its birth to its ultimate fate felt like trying to track a single raindrop in a turbulent storm. That's where the concept of Penrose diagrams started to offer a crucial shift in perspective, a way to translate the mind-bending geometry of black holes into something a little more manageable. Sir Roger Penrose, a brilliant theoretical physicist, realized that the equations governing black hole evolution weren't simply a set of rules operating within three spatial dimensions and time. Instead, they described a four-dimensional block universe, a single, unchanging structure encompassing all of space-time. It's a profoundly counterintuitive notion, but it allows us to represent the incredibly distorted space-time around a black hole with far greater clarity than traditional diagrams. At the heart of a Penrose diagram is the Schwarzschild diagram, named after Carl Schwarzschild, who provided the first exact solution to Einstein's field equations for a non-rotating, uncharged black hole. This diagram is essentially a map of space-time around that specific black hole. The key feature is the event horizon, a boundary drawn in the diagram. It's crucial to understand that the event horizon isn't a physical surface, it's a point of no return. Anything that crosses it, including light, is forever trapped within the black hole. The diagram represents space-time as a grid. The horizontal axis represents time, and the vertical axis represents radial distance from the center of the black hole. The distance increases steadily as you move upwards on the vertical axis. The event horizon is drawn as a curve, a line, that marks the point where the radial distance equals the Schwarzschild radius, which is directly proportional to the black hole's mass. Outside the event horizon, space-time is relatively smooth, but as you approach the horizon, it becomes increasingly curved and distorted. Now, here's where it gets truly fascinating. Penrose envisioned that, theoretically, it's possible to move through space-time in a way that avoids crossing the event horizon. He proposed the existence of a warm throat, a region of extremely high curvature, where space-time is so warped that it's possible to travel directly from one point in space-time to another, bypassing the conventional path through the black hole. This isn't a literal tunnel, it's a trajectory through the warped geometry of space-time. To visualize this, imagine a line extending from the event horizon, but instead of plunging into the black hole, it curves sharply and continues to extend outwards, eventually intersecting with a region of space far beyond what we would normally consider the black hole's influence. This is represented on the Penrose diagram as a time-like curve, a path through space-time that allows a hypothetical observer to travel without being pulled into the singularity. The beauty of the Penrose diagram is that it allows us to represent different evolutionary scenarios for a black hole. For a stationary black hole, one that hasn't been perturbed by external forces, the time-like curve is relatively simple. It starts at the event horizon and extends outward, essentially tracing the path of a traveler who simply wanders away from the black hole. However, things get significantly more complex when you introduce perturbations such as a violent collision with another star. This creates ripples in space-time called gravitational waves, which dramatically alter the shape of the time-like curve. The curve becomes twisted and distorted, representing the chaotic dance of space-time as the black hole interacts with its surroundings. Furthermore, Penrose diagrams provide a framework for considering the eventual evaporation of a black hole, a process predicted by Stephen Hawking's theory of Hawking radiation. Hawking radiation involves the emission of particles from the vicinity of the event horizon due to quantum effects. This radiation effectively carries away energy from the black hole, causing it to slowly shrink and eventually disappear. On a Penrose diagram, this evaporation is represented by a gradually shrinking area enclosed by the event horizon. The time-like curve continues to extend outwards, but the area it encompasses gets smaller and smaller as the black hole loses mass. The diagram doesn't show the details of the quantum mechanics driving the process, but it offers a powerful visual representation of the overall trend, the black hole slowly fading away over an incredibly long period. The use of Penrose diagrams isn't about providing a perfect, complete picture of black hole evolution. They're more like conceptual tools, allowing physicists to explore the possibilities and implications of the extreme physics involved. They highlight the non-intuitive nature of space-time and offer a surprisingly elegant way to understand how black holes can both destroy and ultimately disappear, playing their part in the grand cosmic drama. They demonstrate that even within the darkest corners of the universe, there are patterns and possibilities waiting to be unveiled, if only we have the right tools, like a Penrose diagram, to map them out. The universe, as we understand it, began with an incredible burst of energy, a moment often referred to as the Big Bang. For a fraction of a second, it was a state of pure, unimaginable density everything, and everything that would become, crammed into a space smaller than an atom. Then it expanded and continues to expand still, carrying with it the seeds of galaxies, stars, and ultimately us. The standard Big Bang theory describes this expansion and evolution remarkably well, outlining a gradual process of cooling and formation. However, a fascinating and still somewhat speculative idea has emerged, one that suggests the Big Bang wasn't quite as smooth and uniform as our current models portray. This idea centers around the possibility of primordial black holes, tiny black holes born not from the collapse of massive stars, but from the very first moments of the universe itself. The crucial point is that the early universe was subject to drastically different conditions than what we observe today. Immediately following the Big Bang, the universe was filled with immense fluctuations in density, like ripples in a pond after a stone is dropped in. These weren't just slight variations, they were extreme, chaotic, and incredibly energetic. It's believed that these fluctuations, driven by quantum mechanics and inflation, could have created regions of space where the energy density became so high that gravity simply overwhelmed all other forces. Instead of forming a smoothly expanding spacetime, these regions would have collapsed directly into black holes that formed before stars ever existed. These primordial black holes wouldn't have grown like stellar black holes, feeding on surrounding matter. Their initial size would have been largely determined by the level of fluctuation that triggered their formation. Some might have been microscopic, with masses measured in fractions of a gram. Others could have been considerably larger, perhaps even comparable to the mass of small planets or even larger asteroids. The range of possible initial masses is wide, and this is a key element in understanding their potential impact on the universe. The existence of primordial black holes offers a possible solution to several puzzling observations. For example, dark matter, the mysterious substance that makes up about 85% of the universe's mass, has remained stubbornly elusive despite decades of searching. Perhaps a significant portion of dark matter isn't composed of the weakly interacting massive particles, WMPs, scientists initially hypothesized, but rather consists of primordial black holes. These black holes would move through space at near light speed, undetectable by conventional telescopes because they don't emit light. Their gravitational influence, however, would be readily apparent through their effects on the rotation curves of galaxies, the surprisingly flat speeds at which galaxies rotate. Furthermore, the observed distribution of small mass dark objects, ultra-faint dwarf galaxies, provides a potential link. These galaxies, vastly smaller and fainter than our Milky Way, exhibit rotation curves similar to those predicted by the existence of dark matter. Primordial black holes, especially in the appropriate mass ranges, could explain the formation and observed properties of these enigmatic structures. The theory isn't without its challenges. One significant hurdle is the question of how these fluctuations in density occurred in the first place. While inflation provides a theoretical framework for explaining the initial expansion, it doesn't fully explain the precise magnitude and character of the density fluctuations needed to create primordial black holes. Ongoing research in particle physics and cosmology is actively seeking to understand the fundamental processes that might have generated these initial seeds of black hole formation. Another avenue of investigation focuses on the potential signatures of primordial black holes on the cosmic microwave background (CMB), the afterglow of the Big Bang. The CMB is remarkably uniform, but tiny fluctuations exist, subtle variations in temperature, that could potentially contain information about the early universe. Scientists are searching for specific patterns in the CMB that could be imprinted by the gravitational effects of primordial black holes as they interacted with the expanding spacetime. These patterns, if detected, would be compelling evidence supporting the theory. Models are also being developed that consider how primordial black holes might have influenced the formation of the very first stars and galaxies. It's suggested that these tiny black holes could have acted as gravitational seeds, concentrating matter and facilitating the collapse of larger clouds, ultimately leading to the formation of the first generations of stars. The feedback from these early stellar populations would, in turn, have shaped the subsequent evolution of the universe. The study of primordial black holes represents a frontier in cosmology, a quest to probe the most extreme conditions of the early universe. While the evidence remains circumstantial, the potential implications are profound. It's a reminder that our understanding of the universe is constantly evolving, shaped by new observations and theoretical insights. The idea of black holes born from the Big Bang challenges our conventional notions of cosmic evolution and opens the door to entirely new possibilities about the nature of space, time, and the very origins of everything. The ongoing exploration of this concept continues to provide a deeper, more complex picture of the cosmos and our place within it. The universe, as we've explored, holds secrets that aren't always revealed through light. For billions of years, our understanding of black holes was largely based on their predicted effects. Their immense gravity warping space-time, swallowing up everything around them. But directly observing a black hole, something so dense and dark, seemed almost impossible. Then, a remarkable technological advancement began to offer a completely new way to see these cosmic giants, the detection of gravitational waves. Before this, the only way scientists could truly confirm the existence of black holes, beyond theoretical calculations, was through observing their influence on surrounding matter, tracking the orbits of stars near an unseen heavy object, or observing the accretion disk of superheated material swirling into a black hole. These were indirect methods, reliant on the presence of light, or X, rays emitted from the extreme environment. The challenge was that black holes, by definition, don't emit light themselves. They represent the ultimate endpoint of gravitational collapse, a region where spacetime is so curved that nothing, not even light, can escape. The key to a new detection method lay in Einstein's theory of general relativity, specifically a prediction made almost a century earlier. Einstein had described gravity not as a force, but as a curvature in the fabric of spacetime. He theorized that accelerating massive objects, think of a car speeding down a road, would create ripples in this fabric, much like dropping a stone into a still pond. These ripples are what we now call gravitational waves. He predicted their existence. But the difficulty was that these waves are incredibly faint, stretching and squeezing spacetime in minuscule ways. Detecting them was like trying to sense the movement of a single water droplet in the vast ocean. The Laser Interferometer Gravitational Wave Observatory, or LIGO, was born from this challenge. Located in Louisiana and Washington states, LIGO utilizes a revolutionary technique to measure these distortions. It consists of two L-shaped arms, each 4 kilometers long. At the end of each arm sits a powerful laser. The laser beam is split into two, and each beam travels down its respective arm, bouncing off a mirror at the far end. The mirrors are incredibly precise, reflecting the laser beam back to the starting point. The returning beams are then recombined, and if the arms have been stretched or squeezed by a passing gravitational wave, the interference pattern of the returning beams will subtly change. This change, however tiny, is the signal of the wave. The core of LIGO isn't just the long arms, it's the incredibly sensitive detection system. The mirrors aren't just reflecting light, they're designed to detect changes in the length of the arms, down to a distance smaller than the width of a proton. This precision is achieved through sophisticated electronics and advanced data analysis. The detectors are constantly monitoring for these minute shifts, filtering out noise from vibrations and other environmental disturbances. LIGO wasn't alone in this endeavor. In Europe, the Virgo detector, located in Italy, uses a similar principle but with a different configuration, employing a 40-kilometer long arm and a different method of detecting the changes in laser length. Having two independent detectors, LIGO and Virgo, vastly increases the confidence in any detection. If one detector picks up a signal, the other can be used to verify whether it's a genuine gravitational wave or simply a measurement error. On September 14, 2015, LIGO delivered a groundbreaking announcement, the first direct detection of gravitational waves. The signal came from a cataclysmic event, the merger of two black holes, each several times the mass of our Sun, located approximately 1.3 billion light-years away. As the black holes spiraled inward, they collided with immense force, creating a violent disturbance in space-time that sent gravitational waves rippling outwards, at nearly the speed of light. The echoes of this cosmic collision, faint as they were, had finally been captured by LIGO. This wasn't just a confirmation of Einstein's theory, it opened up a whole new era in astronomy. Suddenly, we could hear the universe in a way we never thought possible. It allowed us to study black hole mergers directly, providing unprecedented information about their masses, spins, and distances. The Virgo detector also contributed to this historic detection, confirming the signal and solidifying the scientific achievement. The implications are profound. This new method of observing the universe, gravitational wave astronomy, complements traditional telescopes that rely on electromagnetic radiation, light, radio waves, X-rays, etc. It provides a completely independent way to study some of the most extreme events in the cosmos, like black hole mergers and, potentially, the very beginning of the universe. Scientists are now actively searching for other gravitational wave signals from neutron star mergers, supernovae explosions, or even primordial gravitational waves generated during the Big Bang. Each detection brings us closer to a more complete understanding of the universe and the enigmatic objects that dwell within it, silent yet profoundly influential. The accretion disk surrounding a black hole isn't just a swirling, chaotic mess of gas and dust. It's a place of incredible complexity, a stage for some of the most energetic phenomena in the universe. While gravity is undeniably the dominant force, pulling everything relentlessly inward, a hidden conductor is at play: magnetism. It's a far more subtle process than the sheer weight of a black hole, but magnetic fields play a crucial role in how material spirals towards the event horizon, shaping the disk itself and dramatically influencing its behavior. Let's consider what's actually happening. When material like gas, dust, and even stars get pulled towards a black hole, it doesn't arrive as a neat, orderly stream. Instead, it arrives in a torrent, a river of particles moving at incredibly high speeds. This material originates from many sources: stellar winds from nearby stars, the debris of disrupted stars pulled in, or even material ripped from the accretion disk itself through violent instabilities. As this material rushes towards the black hole, it's subjected to immense stresses. The particles collide, heat up, and accelerate to astonishing velocities, often a significant fraction of the speed of light. This creates a highly conductive plasma, meaning it's filled with free electrons and ions, constantly moving and interacting with electric and magnetic fields. Now, think about an electrical current. When electric charges move, they create a magnetic field around them. This is a fundamental principle of electromagnetism, described by Maxwell's equations. The accelerating particles within the accretion disk are, in essence, generating their own magnetic fields. These fields aren't uniform, they're tangled and dynamic, constantly changing direction and strength as the particles move. This chaotic dance of magnetic fields is what gives the accretion disk its distinctive structure. Initially, the magnetic fields are primarily generated by the chaotic motion of the plasma. However, as the disk becomes denser and the particle collisions become more frequent, a more organized process emerges. The magnetic fields start to interact with each other, creating a complex network of field lines that wrap around the disk. These field lines become anchored at the base of the disk, where the material is falling inwards, and they extend outwards, threading through the disk. It's like a giant, invisible web. The impact of these magnetic fields on the flow of material is profound. Firstly, they exert a force, the Lorentz force, on the moving charged particles. This force is perpendicular to both the particle's velocity and the magnetic field. This seemingly small force can significantly alter the trajectory of the particles, diverting them from a purely gravitational path. Instead of spiraling directly towards the black hole, particles are forced to follow complex, swirling patterns dictated by the magnetic field lines. This is where the concept of magnetic reconnection comes into play. Because the magnetic field lines are constantly twisting and changing, they can sometimes become unstable and break apart. When this happens, the magnetic field lines reconnect, releasing enormous amounts of energy in the form of heat and radiation. This process is frequently observed in solar flares, powerful eruptions on the sun, and it's thought to be a major source of energy in accretion disks around black holes. The released energy heats the plasma to incredibly high temperatures, causing it to emit intense X-rays and other forms of electromagnetic radiation, making the black hole and its surrounding disk incredibly bright. Furthermore, magnetic fields play a crucial role in stabilizing the accretion disk to some extent. Without them, the infalling material would likely undergo violent instabilities, leading to a highly disordered and turbulent disk, making it difficult for material to actually accrete onto the black hole. The magnetic fields help to channel the flow, creating a more organized, self-sustaining system. Observations of X-ray binaries systems, consisting of a black hole or neutron star orbiting a normal star, provide strong evidence for the importance of magnetic fields. The X-ray emissions from these systems are remarkably correlated with the changes in the magnetic field strength, as seen by X-ray telescopes. The patterns of X-ray emission often reveal the complex structure of the magnetic field within the accretion disk, showing features like coronagraphs, bright rings of emission caused by focused magnetic field lines. The study of magnetic fields in accretion disks is an ongoing area of research, and scientists are constantly refining their models and observations. Understanding these intricate interactions is key to unlocking the secrets of some of the most extreme environments in the universe. It's not just about understanding black holes. It's about understanding the fundamental laws of physics operating under the most extreme conditions, a truly fundamental aspect of how the cosmos works. The interplay of gravity and magnetism within these swirling disks offers a unique window into the behavior of matter and energy at the very edge of space-time. The Milky Way, our home galaxy, isn't a quiet, empty spiral of stars like you might initially picture. It's a bustling metropolis of stellar births and deaths, a gravitational dance of immense proportions. And at its very heart resides a secret, a behemoth lurking in the darkness, Sagittarius A, or Skr A for short. This isn't a typical black hole, not in the way we've often understood them. It's a supermassive black hole, a cosmic giant with a mass approximately 4.1 million times that of our Sun. To truly grasp its scale, consider that our own Sun, a relatively modest star, could orbit Skr A multiple times in a single year. For decades, Skr A was a tantalizing mystery. Scientists knew it had to be there, based on the observed movements of nearby stars. The stars closest to the galactic center were whipping around an unseen object at incredible speeds, far exceeding what a stellar black hole could produce. The orbits wouldn't make sense. They demanded something far more substantial. These stellar dances provided the crucial first evidence, though confirming its existence and properties proved exceptionally difficult. The galactic center is, quite simply, a tremendously crowded region. Dust, gas, and countless other stars create a haze that obscures direct observation. The key to unlocking Skr A's secrets came not through directly seeing the black hole itself, because, let's be clear, no one can see a black hole, but through meticulously tracking the movements of those nearby stars. Astronomers used a technique called astrometry, a very precise measurement of the positions and motions of these stars. Over many years, with data gathered from radio telescopes like the Very Large Array (VLA) and the Atacama Large Millimeter Submillimeter Array (ALMAV) in Chile, a remarkable pattern began to emerge. The stars weren't just moving, they were tracing out incredibly tight, almost perfectly circular orbits around a single, unseen point. This isn't just random chance. The orbits are governed by gravity, and the precision of the measurements confirmed that the gravity was indeed originating from a remarkably compact object, a supermassive black hole. But Skira isn't a still, silent sentinel. It's active, exhibiting bursts of energy that were initially perplexing. For many years, the primary observation was a faint, steady radio emission. This wasn't the expected signature of a quiescent black hole. Instead, every now and then, the radio emission would spike dramatically, increasing tenfold or more, before returning to its baseline level. These events, dubbed flares, were incredibly short-lived, lasting only a few hours, yet they were powerful enough to be detected across vast distances. Scientists eventually realized that these flares were likely caused by material falling into the black hole. Not all of the material plunged straight in. Instead, gas and dust, pulled towards Skira, formed a swirling disk called an accretion disk. As this material spiraled inward, it accelerated to enormous speeds, heating up to millions of degrees Celsius due to friction. This superheated gas then emitted intense radiation across the electromagnetic spectrum, including radio waves, X-rays, and even visible light, which is why the flares were observed. The flares represented periods of intense activity within this accretion disk. The process is remarkably similar to what is thought to happen around stellar, mass black holes, but on a vastly larger scale. The material isn't just swirling around, it's being ripped apart by the black hole's immense gravitational pull. This tidal disruption event, as it's called, creates a powerful, chaotic environment. Moreover, the flares aren't always caused by the entire accretion disk. Occasionally, a small clump of gas or dust would get too close to the black hole, initiating a particularly violent event. The study of Skira provides invaluable insights into the formation and evolution of supermassive black holes. It's believed that these behemoths reside at the centers of nearly all large galaxies, including our own. The prevailing theory suggests they grow over time by accreting vast amounts of gas and dust, or by merging with other black holes. Understanding Skira's dynamics, its flares, its accretion disk, and its interactions with the surrounding stars is therefore crucial to understanding the broader galactic landscape. Furthermore, Skira is a laboratory for testing Einstein's theory of general relativity under extreme conditions. The intense gravitational field around the black hole causes significant distortions in spacetime, and observing these effects provides a unique opportunity to validate or challenge our understanding of gravity. Advanced techniques, like very long baseline interferometries, VLBI, which combines data from multiple radio telescopes spread across the globe, allows astronomers to resolve the region around Skira with unprecedented detail, revealing the intricate structure of the accretion disk and the black hole's influence on its surroundings. The ongoing observations continue to refine our knowledge, unveiling new surprises about this galactic giant and its crucial role in the universe. The universe isn't always silent, even around the most mysterious of objects. While black holes themselves are defined by their profound absorption of light and matter, they can, surprisingly, be incredibly active, blasting out tremendous amounts of energy in the form of jets. These jets, incredibly focused beams of plasma and magnetic fields, originate from the vicinity of black holes, and a key process responsible for their creation and sustained power is known as the Blandford-Znajek mechanism. It's a remarkable demonstration of how gravity, rotation, and magnetism intertwine to create extraordinary astrophysical phenomena. The foundational idea behind the Blandford-Znajek mechanism hinges on the concept of a rotating black hole. It's not simply a point of infinite density as often depicted, but rather a region of spacetime warped by an immense gravitational field. This rotation generates a complex interplay of forces, and crucially, it creates a frame dragging effect. Frame dragging, initially theorized by Albert Einstein, describes how the rotation of a spinning body, like a black hole, drags space-time around with it. Imagine a whirlpool in a river. The water isn't just flowing outwards, but also being pulled in a circular direction by the spinning vortex. Similarly, space-time near a rotating black hole is twisted and distorted, pulling along the magnetic field lines that happen to be present in that area. Now, let's introduce magnetic fields. These fields aren't necessarily pre-existing, they can be generated or significantly amplified within the vicinity of the black hole. This amplification often occurs through a process involving charged particles, such as electrons and protons, that are spiraling inwards towards the event horizon. As these particles accelerate and decelerate within the intense gravitational field, they emit electromagnetic radiation, essentially creating their own magnetic fields. These newly generated fields then interact with the frame dragging effect, creating a self-sustaining feedback loop. The energy for this mechanism doesn't come from the black hole consuming matter. That's a separate accretion process. Instead, the energy arises from the rotational energy of the black hole itself. The black hole's rotation is a fundamental property, and as it spins, it's like a giant dynamo, constantly converting angular momentum into electromagnetic energy. This energy isn't lost, it's channeled through the twisted space-time and amplified by the magnetic fields. Here's where it gets particularly fascinating. The rotating black hole acts like a cosmic battery. The frame dragging forces the magnetic field lines into a helical configuration, wrapping around the black hole. The rotation continues to pull on these field lines, accelerating the charged particles along their length. These accelerated particles generate powerful electromagnetic radiation, radio waves, X-rays, and gamma rays, but more importantly, they carry away angular momentum, effectively slowing down the black hole's rotation. The key to jet formation lies in the concentration of this energy along the magnetic field lines. The accelerated particles, now imbued with enormous kinetic energy, are channeled outwards, forming a focused beam, the jet. These jets can extend for vast distances, sometimes spanning hundreds or even thousands of light years, far beyond the immediate vicinity of the black hole. The Blandford-Znajec mechanism isn't a singular event, it's a continuous process. As the black hole loses angular momentum, the jet continues to be powered by the persistent interaction between rotation, frame, dragging, and magnetic fields. The jet's shape isn't perfectly straight. It often bends and twists, reflecting the complex geometry of the space-time around the black hole. At the base of the jet, where it emerges from the black hole's vicinity, a power jet is often observed, a highly collimated beam with the highest energy density. Further out, the jet gradually widens, with lower energy particles continuing to propagate. Observational evidence for the Blandford-Znajec mechanism is building steadily. Detailed observations of active galactic nuclei, AGNs, where supermassive black holes are actively powering jets, provide compelling support for this theory. The remarkable alignment of the jet's axis with the black hole's spin, coupled with the observed variability in jet power, strongly suggests that the Blandford-Znajec mechanism is at work. Furthermore, simulations of this process, incorporating relativistic effects and magnetic field dynamics, consistently produce jets that resemble those observed in nature. It's important to recognize that while the Blandford-Znajec mechanism offers a powerful explanation for jet formation, it's not the only mechanism involved. Other processes, such as particle acceleration and magnetic reconnection, likely play contributing roles. However, the Blandford-Znajec mechanism provides the foundational framework for understanding how black holes can generate such intensely energetic jets, demonstrating a profound connection between gravity, rotation, and electromagnetism. The universe, even in its most extreme corners, continues to surprise us with its intricate and elegant solutions. The universe isn't always a quiet place. Despite the vastness and seeming emptiness, it's punctuated by some of the most violent, energetic events imaginable. And among these, perhaps the most striking are the mergers of black holes. These aren't slow, graceful dances. They're cataclysmic collisions, occurring across immense distances and at speeds approaching the very limits of the cosmos. Before the advent of gravitational wave detectors, the existence of these events was largely theoretical, a consequence of Einstein's theory of general relativity. Now, thanks to these incredible instruments, we're witnessing them unfold in real time, revealing a hidden symphony of spacetime itself. The process begins with two black holes, initially isolated and orbiting each other. These aren't always perfectly symmetrical pairings. They can be of different masses, spinning at varying rates, and even tilted relative to each other. This initial orbit is governed by the same fundamental laws of physics that dictate planetary motion, but with an immensely stronger force of gravity. As the black holes spiral closer, their gravitational fields become increasingly intertwined, warping spacetime around them in profound ways. The closer they get, the more pronounced this distortion becomes, like ripples spreading across a still pond when a stone is thrown in. What's truly remarkable is that this isn't simply a violent impact. While immense tidal forces are certainly present, pulling material, though not matter itself crosses the event horizon. From each black hole, the primary effect is the alteration of spacetime. The intense gravitational fields create a complex, swirling vortex, a kind of gravitational maelstrom. The black holes aren't smashing together in a single, abrupt moment. Instead, they are constantly adjusting their trajectories, subtly changing their orbits, and influencing each other's spin. This interaction is exquisitely sensitive. Even minute changes in one black hole's rotation can dramatically affect the others. As the black holes draw closer, the gravitational field becomes so extreme that it begins to significantly affect the propagation of light itself. Light, while massless, follows the curves of space-time. Around a black hole, this effect is magnified, leading to phenomena like gravitational lensing, the bending of light around massive objects. But more importantly, the intense gravitational field generates what we now recognize as gravitational waves. These waves are distortions in the fabric of spacetime, propagating outward from the system at the speed of light. Think of spacetime as a giant, invisible trampoline. When a heavy object, like a bowling ball, is placed on the trampoline, it creates a dip. This dip represents the curvature of spacetime. Now, imagine rolling a marble across the trampoline. The marble will curve towards the bowling ball, but it won't necessarily crash into it. Instead, it will orbit around the bowling ball. Now, imagine rolling two bowling balls across the trampoline simultaneously. The resulting ripples, the gravitational waves, are analogous to what happens during a black hole merger. The waves generated by a black hole merger are incredibly complex, far more complicated than the ripples produced by a single object. They aren't simple, symmetrical waves. Instead, they are rich in multiple frequencies, each corresponding to different aspects of the merger process. The frequency of a gravitational wave is determined by the masses of the black holes and their orbital separation. Heavier black holes, for instance, generate lower frequency waves, while those with a smaller orbital separation produce higher frequency waves. The detection of these gravitational waves is a testament to human ingenuity. Instruments like LIGO's Laser Interferometer Gravitational Wave Observatory and Virgo are essentially giant, incredibly sensitive measuring sticks. They consist of two long arms, several kilometers in length, arranged in an L shape. At the end of each arm is a mirror. Lasers are shown from the source towards these mirrors, and the time it takes for the light to return is measured with extraordinary precision. During a black hole merger, the passage of a gravitational wave causes tiny, minute changes in the lengths of the arms. These changes are unbelievably small, smaller than the width of a proton. But LIGO and Virgo are sensitive enough to detect them. When a gravitational wave passes through the detector, it causes a minuscule, but detectable, change in the time it takes for the laser light to travel between the mirrors. This tiny shift in time is then analyzed to determine the properties of the wave, its frequency, amplitude, and polarization. This information allows scientists to reconstruct the dynamics of the black hole merger, revealing details about the masses, spins, and orbital parameters of the merging black holes. The data from these mergers is providing unprecedented insights into the nature of gravity and the evolution of the universe. By studying the waveforms of gravitational waves, scientists can test Einstein's theory of general relativity with unprecedented accuracy, searching for deviations that might hint at new physics. Furthermore, the study of black hole mergers allows us to probe the mechanisms of energy extraction from rotating black holes. Processes like the Blandford-Znajek mechanism, which we explored previously, are thought to be responsible for generating these powerful gravitational waves. The ability to directly observe these cataclysmic events is truly revolutionizing our understanding of the cosmos, one ripple in space-time at a time. The universe, in its grandest dances, always seems to hold a delightful, if perplexing, secret. For centuries, scientists have meticulously charted the movements of stars and galaxies, built increasingly accurate models of gravity, and probed the very fabric of space and time. Yet, when we delve into the most extreme corners of this cosmos, specifically the event horizons of black holes, a fundamental contradiction arises. A dissonance between the two pillars of modern physics, general relativity and quantum mechanics. This contradiction, now widely known as the information paradox, is one of the most profound and actively debated mysteries in all of science, and its resolution may reshape our understanding of reality itself. Let's begin with general relativity, Einstein's masterpiece. This theory describes gravity not as a force, but as a curvature of space-time caused by mass and energy. A black hole, with its immense concentration of mass within an incredibly small volume, creates an extraordinarily deep curvature. It's like placing a bowling ball on a stretched rubber sheet. The sheet dips down, and anything rolling nearby will curve towards it. Once something crosses the event horizon, the point of no return, it's pulled inexorably towards the singularity at the black hole's center. According to general relativity, anything that falls into a black hole, regardless of its composition, a single photon of light, a complex molecule of DNA, or even a massive star, is ultimately crushed and lost forever. All information about that object, including its structure, its quantum state, and its history, vanishes from the universe. It's as if the black hole simply consumes everything, leaving behind nothing but a void. However, quantum mechanics, the theory governing the behavior of matter and energy at the smallest scales, tells a radically different story. At its core, quantum mechanics is built on the principle of unitarity. Unitarity essentially dictates that information is never truly lost. It states that the evolution of a quantum system is always reversible. This means that, in principle, you could always trace back the quantum state of a system and determine exactly what it was like at any point in its past. Think of it like running a movie backwards. You can always rewind and see how the system evolved. Quantum mechanics operates on the assumption that the underlying laws of physics are time-symmetric, meaning they work equally well forwards and backwards in time. Now, Consider the famous thought experiment of a particle colliding with another particle. In quantum mechanics, we can track the collision with perfect precision, recording the exact quantum state of both particles before the collision, and then precisely determining the quantum state of the resulting particles after the collision. The outcome of the collision is completely determined by the initial quantum state, and the process is reversible. However, when this thought experiment is applied to a particle falling into a black hole, the contradiction immediately appears. If a particle falls into a black hole, the information about its quantum state is seemingly erased. But if unitarity is a fundamental law of physics, then that information must somehow be preserved. Where does it go? The prevailing theory, initially proposed by Leonard Susskind and Neil Turok in 1990, suggests that this information doesn't vanish entirely. Instead, it's encoded on the surface of the event horizon itself. This surface, called the holographic screen, isn't a physical surface in the traditional sense. It's a projection of the information contained within the black hole, a kind of quantum hologram. The holographic principle isn't just a theoretical curiosity. It stems from string theory and its implications for understanding the universe's geometry. String theory postulates that the fundamental building blocks of reality aren't point-like particles, but tiny, vibrating strings. These strings exist in higher dimensions, and the dimensions beyond our familiar three spatial dimensions and one time dimension are thought to be curled up in incredibly small ways. The holographic principle suggests that the information about the three-dimensional volume contained within a region of spacetime can be entirely encoded on its two-dimensional boundary. Hawking radiation, discovered by Stephen Hawking in the 1970s, further complicates the picture. Hawking demonstrated that black holes aren't entirely black. They slowly emit radiation due to quantum effects near the event horizon. This radiation, now known as Hawking radiation, causes the black hole to gradually lose mass and eventually evaporate completely. The crucial point is that this Hawking radiation is completely random. It's produced by quantum fluctuations in the vacuum near the event horizon, and it carries no information about the matter that fell into the black hole. If Hawking radiation is truly random and doesn't carry any information, then the black hole's evaporation would seem to permanently erase all the information contained within it, further strengthening the paradox. Recent theoretical developments, however, offer potential resolutions. Some physicists believe that the information isn't actually stored on the holographic screen, but is instead subtly encoded within the Hawking radiation itself, perhaps through correlations between the emitted particles that weren't previously appreciated. Other proposals suggest that the event horizon isn't a solid surface, but rather a fuzzy region of spacetime where the laws of physics become truly bizarre, and information can somehow be preserved in ways we don't yet understand. The information paradox remains one of the biggest challenges in theoretical physics. Solving it requires a deeper understanding of the interplay between general relativity and quantum mechanics, and potentially a radical rethinking of our understanding of space, time, and information itself. The answer, when it comes, will undoubtedly have profound implications for our understanding of the universe and our place within it. For decades, black holes existed primarily as theoretical monsters, objects of mathematical elegance and terrifying gravity. We could predict their behavior, calculate their effects on surrounding matter, and even detect their influence through gravitational lensing, the bending of light around massive objects. However, until relatively recently, we'd never actually seen one. That changed dramatically with a truly remarkable collaboration and a technological feat of unprecedented scale, the Event Horizon Telescope, or EHT. The core idea behind the EHT isn't about pointing a giant telescope at a black hole and snapping a picture like you might a distant galaxy. Instead, it's about creating a single Earth-sized telescope. Black holes, being incredibly distant, appear incredibly small in the sky. To gather enough light to form an image, you need a telescope with an aperture the diameter of its primary collecting surface that's comparable to the size of the black hole itself. The Earth, with its rotation, effectively provides that enormous collecting surface. The EHT isn't a single, monolithic instrument. It's actually a network of 8 telescopes scattered across the globe from Hawaii to Chile to Spain, each equipped with a specialized receiver. These receivers don't capture light directly. They capture radio waves. Black holes don't emit visible light because, well, nothing can escape their immense gravity. But they do emit a different kind of radiation radio waves. These radio waves are generated by the extremely hot, swirling gas, the accretion disk, that surrounds the black hole as matter spirals inwards, heating up to unbelievable temperatures. These 8 telescopes don't work independently. Each one transmits its data to a central processing site in Green Bank, West Virginia. Here, the data from all 8 telescopes is synchronized and combined, creating a single, virtual telescope the size of the Earth. This is achieved through a clever technique called interferometry. Essentially, each telescope acts as a tiny antenna, and by precisely timing the arrival of the radio waves, scientists can pinpoint their location in the sky with incredible accuracy. The process is akin to trying to locate a small object on the ocean using multiple ships. Each ship sees the object from a slightly different angle, and by comparing their observations, they can determine the object's precise position. Similarly, the EHT combines the data from its telescopes to create a super-resolution image far exceeding the resolution limit of any single telescope. The first image of a black hole, released in 2019, was of the supermassive black hole at the center of the galaxy Messier 87's M87. This wasn't a direct picture of the black hole's event horizon, that boundary beyond which nothing can escape. Instead, it was an image of the shadow cast by the black hole against the bright glow of the accretion disk. This shadow is a surprisingly simple shape, a bright ring with a dark central region. The bright ring is formed by light from the accretion disk that is bent and amplified by the black hole's intense gravity. This is a phenomenon predicted by Einstein's theory of general relativity. The dark center represents the region where light is so warped that it doesn't escape, creating a void in the image. The size of the shadow is directly related to the black hole's mass. The more massive the black hole, the larger the shadow. The image of M87's shadow wasn't just a pretty picture, it was a profound validation of Einstein's theory. It provided the first direct observational evidence that black holes truly behave as predicted by general relativity. Furthermore, the EHT team meticulously analyzed the shape and intensity of the shadow, allowing them to precisely measure the black hole's mass and spin. The team discovered that M87's black hole was spinning, a key piece of information that dramatically affected the way light was warped around it. Following the M87 image, the EHT team turned its attention to our own galaxy's supermassive black hole, Sagittarius A Sears, Sagittarius A's, located at the center of the Milky Way. Obtaining an image of Sagittarius A was considerably more challenging than M87, because Sagittarius A is much closer to Earth, making its appearance in the sky far more subtle. The accretion disk around Sagittarius A is fainter and more turbulent, providing less easily discernible data. Despite these difficulties, in 2022, the EHT team announced the first image of Sagittarius A, revealing a remarkably similar shadow to that of M87. The fact that both M87 and Sagittarius A produced shadows of nearly identical shapes suggests that the fundamental physics governing black holes is likely the same throughout the universe. The EHT's ongoing observations are providing unprecedented insights into the behavior of these enigmatic objects, helping scientists to better understand the relationship between gravity, space, and time. The future of the EHT is bright, with plans to observe even more black holes and to further refine our understanding of the universe's most extreme phenomena. The ongoing data collection and analysis promises even more astonishing discoveries in the years to come. The Event Horizon Telescope's stunning image of the black hole at the center of galaxy M87 wasn't just a photograph, it was a tantalizing glimpse of a region utterly unlike anything we routinely experience. But what lays inside that event horizon? That's where things get incredibly tricky, and where the scientific community has shifted its focus from simply observing the edge of these cosmic behemoths to building theoretical models of what their interiors might be like. Because, let's be honest, the event horizon doesn't really tell us anything about the space beyond it. It's simply a boundary. Our current understanding of gravity, Einstein's general relativity, beautifully describes how gravity affects space-time, warping it around massive objects. But when we push general relativity to its absolute limit, the singularity at the center of a black hole, the equations break down. They predict infinite density and space-time curvature, a situation most physicists believe isn't a physically realistic outcome. So, we need to explore alternative ideas, and these models aren't just wild guesses. They are informed by quantum mechanics, thermodynamics, and a healthy dose of mathematical ingenuity. One prominent idea, stemming from the work of physicists like Stephen Hawking, is the concept of a firewall. Initially conceived as a desperate attempt to resolve the information paradox, the apparent loss of information that seems to occur when matter falls into a black hole, the firewall proposes a region of incredibly high energy particles just inside the event horizon. This would effectively incinerate anything that crosses the boundary, preventing the information paradox by completely destroying the infalling matter before it could ever reach the singularity. It's a dramatic picture, but it highlights the deep tensions within our theories when confronted with such extreme conditions. However, the firewall is now largely considered an overcorrection. It introduces a new problem: instantaneous destruction, and many physicists are seeking more gentle solutions. Another avenue of research involves the concept of a quantum foam interior. Quantum mechanics, at its heart, describes the universe as being fundamentally uncertain at the smallest scales. Particles constantly pop into and out of existence, fluctuating between different energy states. Applying these quantum principles to the extreme conditions within a black hole suggests that spacetime itself might be similarly fluctuating, a turbulent sea of virtual particles and warped geometry. Imagine, if you can, a microscopic landscape within the black hole, not smooth and unchanging like the space we're used to, but constantly bubbling and changing, influenced by quantum uncertainties. This isn't necessarily a solid object. It could be more like a probabilistic cloud, where the location and properties of matter are defined only by the probabilities of different states. Calculations based on these ideas suggest that the singularity might be smoothed out, becoming a region of extremely high density but finite curvature, a quantum singularity. Another, more exotic, possibility comes from the theory of wormholes. Wormholes, also known as Einstein-Rosen bridges, are theoretical tunnels connecting two distant points in spacetime. Some physicists speculate that the interior of a black hole could be a wormhole, leading to a region of spacetime far removed from our own. Falling into a black hole might not lead to destruction, but to a journey through this hidden shortcut, potentially connecting our universe to another, entirely different one. Of course, the stability of such wormholes is highly questionable. Any matter entering them would likely cause them to collapse instantly. Furthermore, research is exploring the role of information itself. The idea is that information isn't truly lost when it falls into a black hole, but instead is encoded in the quantum state of the event horizon. This horizon, constantly fluctuating due to the intense gravity and quantum effects, might act as a kind of cosmic memory bank, storing the information of everything that has ever fallen in. This connects back to the information paradox and suggests that a complete understanding of black hole interiors requires a more unified theory of quantum gravity, one that seamlessly blends general relativity and quantum mechanics. String theory offers one potential path towards this unification. String theory proposes that fundamental particles are not point-like, but rather tiny, vibrating strings. In the extreme gravity environment of a black hole, these strings could potentially resolve the singularity, creating a more complex, multi-dimensional structure. The mathematics involved is incredibly complex, and it's difficult to make concrete predictions about the details of this interior, but it suggests a fundamentally different architecture than the simple singularity envisioned by general relativity. The study of black hole interiors isn't just about understanding these fascinating objects. It's pushing the boundaries of our knowledge about the very nature of space and time. It's a reminder that our current theories are incomplete, and that the universe likely holds secrets far stranger than we can currently imagine. The quest to model the interior of a black hole is a journey into the unknown, driven by the fundamental desire to understand the most extreme conditions in the cosmos and, ultimately, the origins of space and time themselves. As our technology advances and our theoretical understanding deepens, we move closer to potentially unlocking one of the universe's greatest mysteries. The whispers started subtly, circulating amongst a group of theoretical physicists in the late 2000s, a ripple of unconventional thought around the stubbornly, persistent problem of information loss within black holes. The Event Horizon Telescope's success in capturing images of the shadow of M87, a supermassive black hole, hadn't resolved the fundamental conflict between Einstein's theory of general relativity and the tenets of quantum mechanics. The existing approaches, firewalls, fuzzballs, remnants, were generating immense heat and theoretical complexity, each battling for prominence but failing to achieve a truly satisfying resolution. Then came Joshua Fisher. Fisher, a brilliant mind at the University of California, Berkeley, had spent years meticulously studying the behavior of quantum fields in curved spacetime. His particular focus was on the way these fields, the very fabric of reality described by quantum mechanics, interact with gravity, specifically the gravitational field around a black hole. He'd been investigating a problem first proposed decades earlier by David Duyach, a pioneer in quantum computation, but hadn't achieved widespread recognition until he began to explicitly link it to black hole physics. Duyach's initial suggestion was that the information about matter falling into a black hole wasn't truly lost. It was subtly encoded within the black hole's own structure, reflected in the quantum fluctuations of the spacetime surrounding the event horizon. Fisher took this idea and built a detailed mathematical model, what he termed the Black Hole Information Reservoir, or BHI. Unlike many other models that envisioned a singular, discrete object representing a black hole, a point of infinite density, Fisher's model conceived of a black hole as a constantly fluctuating quantum reservoir. He argued that the event horizon wasn't a static boundary, but rather a region where quantum fields, particularly those describing the energy of photons, were continually undergoing intense, unpredictable fluctuations. These fluctuations, he proposed, acted as a kind of memory storage. The core of the BHI model lay in the concept of quantum entanglement. Played out on a truly grand scale, Fisher's equations showed that the immense gravitational field of a black hole would inevitably entangle the quantum states of all the particles near the event horizon. Think of it like this: imagine a vast, intricately woven tapestry. Each thread represents a quantum state, and the black hole's gravity pulls these threads into a complex, interconnected pattern. This entanglement, he argued, was the mechanism by which information about the infalling matter was preserved. As particles spiraled towards the horizon, they became inextricably linked with the black hole's quantum state, essentially contributing to its overall structure. Crucially, Fisher's model didn't predict a specific, localized location where information was stored. Instead, he suggested the information was distributed throughout the entire black hole's quantum structure, a diffuse, interwoven network. The event horizon itself wasn't a barrier preventing information escape. It was simply the point at which the entanglement process became overwhelmingly dominant. This was radically different from models suggesting a singularity at the center, a point of infinite density and therefore infinite capacity for information storage, a concept that increasingly felt strained under the weight of quantum mechanics. However, the BHI model immediately generated considerable controversy. The initial calculations were extraordinarily complex, requiring sophisticated numerical simulations to verify Fisher's predictions. Critics questioned the validity of extrapolating quantum field theory, typically dealing with relatively small scales, to the extreme gravitational conditions near a black hole. Some argued that the model's reliance on perfect, lossless entanglement was physically unrealistic, a mathematical convenience rather than a genuine reflection of reality. Others worried about the potential for the model to introduce new, unobservable degrees of freedom into the universe. Furthermore, the model's mathematical framework leaned heavily on the assumption of a specific, highly ordered quantum state at the event horizon. This assumption, critics pointed out, was itself a significant extrapolation from our current understanding of quantum field theory. If the true state of the event horizon was more chaotic and less precisely defined, the BHI model's predictions could become unreliable. The sheer scale of the model's calculations also made it difficult to test experimentally. There was no obvious way to directly observe the subtle fluctuations Fisher predicted. Despite the skepticism, Fisher's work remained a vital contribution to the ongoing debate. His model forced physicists to reconsider the fundamental relationship between gravity and quantum mechanics, highlighting the profound challenges inherent in reconciling these two pillars of modern physics. The controversy surrounding the BHI model didn't resolve the information paradox, but it deepened the exploration of the problem, revealing previously unconsidered aspects of black hole physics and driving further theoretical development. As research continued, refinements to Fisher's initial model emerged, incorporating elements from other approaches and ultimately contributing to a more nuanced and hopefully a more complete understanding of these enigmatic cosmic giants. The universe, as we've explored, is a place of astonishing extremes, dominated by objects with gravity so potent it bends space and time itself. Black holes, remnants of collapsed stars, or perhaps born from the very beginnings of the cosmos, are at the heart of these extremes. But their existence raises a profound and surprisingly philosophical question. What if the information about these cosmic behemoths, about the matter that formed them, and the events that led to their creation, simply vanishes? This is where the concept of cosmic censorship enters the story, a daring hypothesis attempting to resolve a deep conflict between our understanding of gravity and the fundamental laws of physics. For decades, physicists wrestled with a paradox known as the information loss problem. General relativity, Einstein's theory of gravity paints a remarkably clear picture of black holes. It describes them as regions where the gravitational field is so strong that nothing, not even light, can escape. The event horizon, the boundary beyond which escape is impossible, is a one-way membrane. Once something crosses that line, it's gone, swallowed forever. But quantum mechanics, the theory governing the behavior of matter at the smallest scales, insists that information cannot be truly destroyed. It states that information always exists, encoded within the quantum states of particles. The problem arises because, according to general relativity, anything that falls into a black hole is lost. The black hole grows, increasing its mass and radius. But the original information about that object, its composition, its state of motion, seems to simply vanish. This contradicts the core principle of quantum mechanics. If information is lost, it throws a wrench into one of the most fundamental building blocks of physics. It suggests that the universe isn't self-consistent, that reality might be fundamentally flawed. The idea of cosmic censorship, first proposed by physicist Igor Novikov in the 1990s, offers a potential solution. It suggests that the laws of physics conspire to prevent us from ever observing the singularity, the infinitely dense point at the heart of a black hole. Novikov proposed that the singularity is always hidden behind a horizon of unbroken causality. This means that no matter how close we might get to observing the singularity, we'll always be prevented from seeing its details. It's like a cosmic firewall, a theoretical barrier maintained by the very fabric of spacetime. The reasoning behind this censorship isn't based on a specific physical mechanism, but rather on a profound symmetry. Novikov believed that if the universe were truly open, if singularities were visible, it would lead to profound paradoxes and contradictions. The potential for time travel, for instance, becomes significantly more probable, and the consequences would be utterly chaotic. The universe, according to this view, would actively prevent such a scenario. Now, let's consider the implications for the future of the universe. Black holes, and particularly primordial black holes, those potentially formed in the very early universe, could play a crucial role. As the universe continues to expand at an accelerating rate, driven by dark energy, these black holes are gradually losing mass as they emit Hawking radiation, a theoretical process where black holes slowly evaporate over immense timescales. But the question remains, what happens to that evaporated matter? If cosmic censorship holds true, the remnants of these black holes, their constituent particles, won't simply disperse into the surrounding space. Instead, they will remain hidden, effectively erased from our observable universe. This has profound implications for the long-term fate of the cosmos. Some theories propose that black holes could be the seeds for the formation of new universes, baby universes, within our own. Within the event horizon, the extreme gravitational forces might create conditions allowing for quantum fluctuations to trigger new space-time bubbles, potentially leading to a multiverse. However, if cosmic censorship is in effect, these new universes would also be shielded from our observation, their details permanently obscured. Furthermore, the fate of black holes is intricately linked to the eventual heat death of the universe. As the universe expands and cools, eventually all usable energy will be dissipated, leaving behind a state of maximum entropy, a state of complete disorder. Black holes, even as they slowly evaporate, are effectively resisting this entropy. They represent a concentrated form of energy and information, and their continued existence, if shielded by cosmic censorship, could delay the onset of heat death, albeit slightly. The exploration of black holes isn't just about understanding these cosmic enigmas, it's about probing the deepest assumptions about reality itself. Cosmic censorship isn't a proven theory, but it represents a fascinating attempt to reconcile the seemingly contradictory realms of gravity and quantum mechanics. It's a reminder that the universe may hold secrets far beyond our current comprehension, secrets guarded by an unseen, and perhaps profoundly elegant, cosmic firewall. As we continue to observe black holes with ever-increasing precision, and as our theoretical models become more sophisticated, we may one day gain a deeper understanding of whether this censorship is a fundamental aspect of reality or simply a placeholder until we unlock the universe's ultimate truths. If these stories help you rest, consider subscribing and sharing them with others who seek calm. We've journeyed through the depths of black holes, a place of immense gravity and silent wonder. Let your thoughts drift, calm and unhurried, like stardust in the darkness, until sleep embraces you.